If you're a developer, you write functions all the time. But have you ever really stopped and thought about what's going on under the hood when you call one? Well, in this explainer, we're going to pull back the curtain and dive deep into the secret life of a function call.
So let's get right into it. We are going to follow the entire journey from the moment you write the code to how the computer actually handles it, all the way to the second it gives you a value back. It's a pretty fascinating trip, so stick around.
You might think our journey starts with the function call itself, but nope. It actually begins with the blueprint, the function's definition, and probably the most critical part of that blueprint, the thing that acts like a map for anyone reading your code, is its name.
I mean, just look at the difference a good name makes. A function does something, right? It performs an action. So its name really ought to be a verb. Something like handle is, well, it's lazy. It leaves you guessing. But handle forms submit? Now that tells you exactly what's about to happen. The code basically documents itself.
And the same exact idea applies to the data your function works with. These weird cryptic abbreviations like USRM, sure, you might save 2 keystrokes today, but I promise you it's going to cost you and your team minutes, maybe even hours of confusion down the road. Clarity is always, always a better investment.
At the end of the day, it all just boils down to consistency. Whether your team likes camel case for JavaScript or snake_case for Python, the most important thing is that everybody sticks to the plan. It just makes the whole codebase predictable and so much easier to get around in.
Okay, so our blueprint is ready. It's time for the call to adventure. When we actually use the function, we need to give it some info. And this brings us to a really key distinction that honestly trips a lot of people up: the difference between arguments and parameters.
The easiest way to think of a parameter is like a designated parking spot. It's defined right there in the function's blueprint, it's got a name, and it's just sitting there, waiting for a car to show up. It's a placeholder.
Here we go, perfect example. In this sum function definition, addend1 and addend2, yep, those are our parameters. They are the named placeholders, those empty parking spots we were just talking about, waiting inside the function's blueprint. Okay, so if the parameter is the parking spot, then the argument is the actual car that pulls into it. It's the real, actual value or variable that you give the function when you call it.
And here's the other side of that coin. In the function call, value 1 and value 2 are the arguments. They're the actual cars driving into our parking spots. They're the real data getting passed in. So just remember, parameters are in the definition, arguments are in the call.
All right, so we've called our function, we've passed in our arguments, but where does the computer actually do the work? Well, it all happens in a special, super organized part of the computer's memory called the call stack. The call stack works just like a stack of plates. You put a new plate on top, and when you need one, you take the top one off first. This whole last in, first out, or LIFO system is just the perfect way for a computer to juggle function calls. So when your program first kicks off, the main function, we'll just call it main, is the first thing to run. It gets its own little workspace, which is called a stack frame, and that gets placed at the very bottom of our stack of plates. Now let's say our main function calls another function, maybe one called add. A brand new stack frame for add is created, and pam, it's pushed right onto the top of the stack. This is our new top plate. The program totally pauses what it was doing in main, and its entire focus is now on running the code inside this new add frame. So once add finishes its job and returns a value, it's done. Its stack frame gets popped right off the top of the stack and just disappears. And just like that, control goes right back to the main frame, which can now pick up exactly where it left off. So what's inside each of these little boxes? Well, basically, it's everything a function needs to do its thing. The arguments it got, any local variables it creates for itself, and, this is crucial, the return address. That's like a bookmark telling it exactly where to go back to when it's done. Oh, and here's a fun fact. This stack isn't infinitely big. If you accidentally write a function that calls itself over and over and never stops, that's called infinite recursion, you'll just keep pushing frames onto the stack until you run out of room. And that's a stack overflow. Sound familiar? Now you know exactly where that error comes from. Now, how the data gets into that frame is super important. With call by value, the function gets a copy of your data. Think of it like a photocopy. It can write all over the copy, scribble on it, whatever, but your original document is perfectly safe. With call by address, though, the function gets the actual keys to the original file cabinet. It can go in there and change that original data, which can be powerful but can also cause some really weird bugs if you're not careful.
Okay, so far we've just been passing simple things as arguments, numbers, strings. But what happens if we level up? What if the argument we pass into one function is another function? This, my friends, is where things get really powerful.
Oh man, we have all been here. You write a couple of functions, like calculate area and calculate diameter, and then you step back and realize they're almost the exact same function. The loop is the same, the setup is the same, the only difference is one tiny piece of logic. This kind of repetition is a huge red flag that we can do things in a much smarter way.
And that smarter way is by using something called a higher order function. So instead of writing two big, clunky, repetitive functions, we pull out that unique logic into its own small, focused function. Then we create one generic function, let's call it calculate, that can accept that little logic function as an argument. It is just such an elegant and clean way to write less code.
And you know what? You're probably already using higher order functions and you don't even know it. Common built-in functions like map, filter, and reduce are perfect examples. Map transforms every item in a list. Filter picks out just the items you want, and reduce boils the whole list down to a single result. They all work by taking a function as an argument.
So we followed this whole journey, right? From naming things properly to the call stack and even functions that take other functions for a ride. But what's the point? Why does understanding all this stuff actually matter when you sit down to write code?
Here's the big takeaway. Knowing what's happening behind the scenes lets you write code that's not just working, but is actually good. Your code becomes more readable because you pick better names. It becomes way easier to debug because you can literally picture the call stack in your head. It's more efficient when you use patterns like higher order functions. And all of that makes you a better teammate and a more effective developer.
This knowledge really changes how you see your work. You stop just telling the computer what to do, and you start to understand how it thinks. Thanks for joining me on this explainer. What complex topic should we break down next?